All right, hello, my name is Jasper Tinas. I'm in Math32 section 20, discussion section 25D, and this is during the spring semester of 2021. Today I'll be going over the Monty Hall problem. Basically what the Monty Hall problem is it's derived from a game show called Let's Make a Deal, and it features its host, Monty Hall. And the idea of this game show is that you're posed with a certain amount of doors. In this case, we'll say 3, and you have to determine which of these doors has the prize behind it. In this case, a sports car. So behind one of the doors is a sports car. Behind the other 2 doors are goats. And so let's say that we chose door number 1 as having the sports car behind it. Now, Monty Hall, as a rule of thumb, reveals one of the doors that has a goat behind it, in this case, door 3. And so he gives us the option to switch from door 1 to door 2, or to just stick with our initial bet of door 1 having the car behind it. So the question we ask ourselves is, do we gain an advantage by switching our initial choice? And this has to do with the entirety of the Monty Hall dilemma. And so let's go over this in an example. Let's say we have 3 doors again. This time we're going to say that the 3rd door has the car behind it. And so if we choose the 3rd door, Monty Hall chooses one of the doors that has the goat behind it, in this case, the 1st door. And so, we're asking ourselves, what are the chances that the 3rd door has the car behind it versus the 2nd door? What's the probability there? Is it 50-50? If we break this down, we can see here that there's 1/3 probability associated with door 3 if we stick with it having the car, versus 2/3 for a cumulative probability for door 1 and door 2. Now, if we look at this in more depth, we can see that since door 1 has a goat behind it that's been revealed to us, we can attribute 0 probability to it having the car behind it. As door 2 is the only one left there, we can attribute or we can accumulate door 2 with the remainder of the 2/3 probability. And now we can see an imbalance in probabilities between door 2 and door 3. So now if we stick with door 3, sure enough, we see that door 3 has the goat behind it. So going back to our initial question, do we gain an advantage by switching our initial choice? We can say that yes, in this case, we do get an advantage. And in this case, we gain an advantage of exactly 1/3 going from door 3 to door 2 in choosing the correct answer. So fleshing this out with a more hands-on calculation, we can see our initial choices on the left side. Those aren't revealed to us. Those are just simply to indicate that we chose them. So in the first tree, we can see that Monty Hall is the idea of he can have the choice of either revealing door 2 or door 3, you might say, or in the second tree, he might reveal door 1 or door 3. And finally, in the third tree, either door 1 or door 2. And you might say, at first glance, that each of these branches has a 1/2 probability of occurring, given that there are 2 doors, 50-50 chance between them being revealed. And multiplying from left to right, we can see that each branch has a 1/6 probability of occurring in that order. And so you might say this at first glance when it is in fact incorrect. As we've gone over previously, Monty Hall only reveals a door that has a goat behind it and not a door that has a sports car behind it. So we can rule out the first and last branch. And so we're left with the 4 branches in between. And so now if we multiply across, we see that the first tree has a total probability of 1/3. And that is the same case with the last tree. So in both trees where both goats are revealed to us. Now they're not revealed, we just know that both goats are on the table there. We have a cumulative 2/3 chance of switching and choosing the sports car. Now, in the middle tree, we can see here that if we flesh this out and we see the probabilities here, we still only have a 1/3 chance of getting the sports car. So, and that just goes to support our initial example. So moving on, what are some real world applications of this problem? So other than, of course, the fact this is based on a game show, and going into a game show, you can use this very problem as a way to kind of predict what door will have what behind it. We can relate this problem to the law of total probability. Now, this is from the textbook. And we can say that based on this formula, we can also attribute this to real world dilemmas such as COVID testing. And so we could say, we can actually get an idea of the probability that someone has tested positive, being that they are COVID-19 positive in reality versus they have tested negative when they actually do have COVID-19. So that's kind of an example of something that is familiar and related to the Monty Hall problem. All right, I hope that sheds some light on the topic of the Monty Hall problem. Works cited here I used were the Monty Hall problem page on Wikipedia, a modern introduction to probability and statistics, the textbook on our homepage as a PDF, and finally the math behind Monty Hall problem on YouTube. Thanks for watching.